getting old, but that's okay. I made it. I'm here. So, yep. And I think what she's doing is she's sticking her tongue out saying, screw COVID. So, all right. So everybody should be here soon. Let me bring up the lecture notes. Okay, wow, there it is. Okay. And everybody can see 3B February 10th, right?
Yes.
Good. All right, well, it's 24 students. Just give it a moment. All right, we're at 28. My last class, we went through the lecture fairly quickly, but I also spent time introducing the Japanese scanner for the project we'll be doing, part A, and how it kind of relates to the finite automaton that I'm going to present to you tonight. So we're going to wind up having a full class, but it's good because it will introduce you to what you'll be working on when you get to the project, which the first part is due March 15th, which is 5 weeks from now. All right, so we looked at grammar back on Monday, and we looked at the production rules. And now what we're going to do is we're going to look at several types of grammars. You're going to recall that we used V to represent our variables, our non-terminals. We said T was our terminals. And then I said that N was some combination of non-terminals and terminals. So I'm going to introduce you to 4 grammar types. We're going to call them grammar type 0, 1, 2, and 3. The first one, type 0, is considered the unrestricted grammar. It's the largest set. Non-restriction grammars, when we look at those production rules in terms of, sorry about that, in terms of X going to Y for the production rule, basically on the left, X, you have to have at least one non-terminal. And then on the right, you can have any combination of terminals, non-terminals, and epsilon that we talked about. And some examples of what grammar rules could look like with these type 0 unrestricted. Again, we've got A non-terminal SBB going to ACBB, or AB going to A terminal B followed by non-terminal B, or A going to epsilon. So any combination. We're not going to use type 0 and type 1 for this class. We're going to be using type 2 and type 3, as you'll see, but we still want to talk about these grammar types. So again, we talk about type 0 being the largest set, unrestricted. And next, we're going to move inside of that largest set, and we're going to have type 1, which we call context sensitive, as well as monotonic. So a grammar is considered monotonic if the size on the left of the production rule is less than or equal to what's on the right-hand side of the production rule. So the length, as you go through the derivation path, as we did on Monday, the length will never decrease. It will always increase. So an example is AB going to D is not allowed. You cannot have a smaller production. And A going to epsilon is not allowed in a context-sensitive grammar. So I know we talked about A going to epsilon last week when we looked at our recursive grammar production rules, and we went to epsilon to end it. But when we talk about the grammars and the languages that we're going to use in this class, you can actually see that we will not have epsilon on the right. So again, we're talking about our type 1, which is known as context sensitive. And it's considered context sensitive if every production in P, where P being that set of production rules, is in the form where you have, in this case, you see XAZ going to XYZ. What that's telling us is that the A is being changed to a Y as it relates to having an X before the A and a Z after the A. Okay? So the X and the Z are anything, and they may not be there. In this case, they are there. The Y cannot be epsilon, and it's anything in terms of n to the plus, which means that it's going to be at least one object and any combination of terminals and non-terminals. And A, which is on the left side of the production rule, is a non-terminal that derives to one or more symbols. In this example, A derives to one symbol, Y. Some examples of context-sensitive grammars are ASB going to ABB. So that S on the left-hand side is being changed to the non-terminals A and B in context to the small a terminal and small b terminal being there. And the next example showing ASB going to ACCB, where the S is changing to the terminals CC. So we talk about a context-sensitive language always increasing in size and or being the same or increasing. Therefore, context-sensitive language implies that it's monotonic. So we looked at type 0, unrestricted, type 1, which we will typically call context-sensitive. We don't use the term monotonic, but we wanted to present it here. The next two grammar types, language types, are your context-free and your regular. Now, a context-free grammar is in the form where A, which is a non-terminal, goes to something on the right, which is going to be at least one or more, a combination of terminals and non-terminals. So only a single non-terminal will appear on the left for a context-free grammar. You'll never have epsilon on the right. And some examples of context-free production rules is a single non-terminal going to a series of terminals and non-terminals. So this is the format of context-free grammars. And I'll explain momentarily where we're going to use those context-free grammars. And a context-free grammar generates a context-free language. So that's type 2, context-free, type 1, context-sensitive, type 0, unrestricted. Now we're going to look at type 3, our fourth grammar. We call that the regular grammar. It produces a regular language. It's the smallest set. And I'm going to show you, which is part of your homework assignment, the Chomsky hierarchy that you're going to be filling in for these 4 languages. For a regular language, every production in P, that set of production rules, is going to be in one of 2 forms. It's either going to be a non-terminal going directly to a terminal, or a non-terminal going to a terminal, which can also be followed by a non-terminal. And that's it. These are the only 2 types of production rules that you're going to find for a regular language. And again, epsilon will not be on the right. So some examples of regular grammars are simply, again, a single non-terminal. Here you see S or A or B, either going to a single character like a 0 or a 1, or going to a 0 or a 1 and then being followed by another non-terminal. And regular grammars generate regular languages. So for the homework assignment, you're going to produce this diagram, and you're going to identify the, actually, I'll bounce to the homework assignment. It's in the wrong window, so it's probably going to stop sharing. It's paused. Let's try that again. Okay, we talked Monday about the different production rules here. Here, you're going to draw that diagram, Chomsky's hierarchy, type 0 on the outside, the innermost being type 3. And what I'm asking you to do for the outermost, which is your type 0, you want to provide the grammar type name and the language type name. And then for the next 2 inner ones, which we're going to focus on for this class, which is our context-free language and our regular languages, you're also going to provide me the automaton type and the compiler part, which we're going to get to momentarily. So there's always going to be an algorithm recognizer for any context-sensitive grammar. Context-sensitive language is recursive, unlike we talked about procedures, which are recursively enumerable and may get stuck. And note, because of that hierarchy, that context-free languages and regular languages are part of context-sensitive languages. So therefore, for context-free languages and regular languages, we're also going to have algorithm recognizers. So what I referred to in the homework, where I want you to talk about the compiler type part and the recognizer, here we talk about, for a regular language, excuse me, it's being used for the tokens in a programming language. This is the scanner part. For the homework assignment, for this week, you're writing the recognizer to see that the string passed in is a binary number. So you're looking to see if it accepts a 0 or a 1. If you put in a 2 or a 3, it fails. So that's where we would use a regular grammar for the scanner to parse the string. And I'm going to show you how we're going to do this for the Japanese parser for the project. So regular languages, type 3, that smallest innermost part of the Chomsky hierarchy, is the regular language, which is used for the scanner or the lexical analyzer. Next one out is our type 2 grammar. It's the context-free grammar, which we also call the context-free language. And that's used for statements in programming languages. This is for the parser and the syntax analyzer, which is where we need some memory. So for the type 3, I talk about a finite automaton or a finite state machine. The acronym finite state machine, FSM, finite automata, FA, that has no memory. When we talk about a context-free language, we're going to use what's called a push-down automaton. A push-down automaton is different than a finite automaton because a push-down automaton allows you to have memory. One of the things that we've beat with a hammer is this A to the N, B to the N. In order to create an automaton that will accept any string that satisfies this expression, you need to know how many A's you had to then make sure you've got the same number of B's. We cannot do that with a regular language because we don't have the memory. You can do it with a context-free language, with a push-down automaton, because it has the memory that's going to allow you to count how many A's you have, and then you'll be able to see if you have the same number of B's. Okay, so throughout the semester, we're really going to beat on A to the N, B to the N. Again, it is a context-free grammar, not a regular grammar. So we talk about an automata being an abstract model for the recognizer, for the parser. We're going to use the automaton to conceptually represent a recognizer of a language before we write a program. So in a way, the automaton is our model. It's the design. It's what's the machine going to look like that we're going to build to determine if the string is accepted by the automaton. And as you saw above, we have different types of automaton. You have your FA, finite automaton, or finite state machine, or the push-down automata. Automaton is an abstract theoretical model of a digital computer. So when you look at an automaton, it has the following components. It has your input tape, which basically reads in every character left to right, one at a time. Then it's got the control unit, much like your CPU in a computer. And it's going to have a state machine that's going to transition from one state to the next based on the character that is read in. So you might have state 1, state 2, state 3, and I'm going to show you very simple examples of a finite automaton state machine. You're going to want to be able to output a yes or no, whether you accept or reject the string. You're doing this on Friday, or you're doing this now for the homework for the recognizer, where if the string that's passed in, if it contains only binary digits, zeros and ones, you return yes, it's in L the language. If it's not, you return no, it's not in the language. So there's our yes, no, that's the output of the finite automaton. So in a way, you are writing code that is a finite automaton that's accepting zeros and ones. And you might have optionally a storage device that can actually read and change storage cells one at a time. And as I mentioned, you will have that with push-down automatons, but not with finite state machines. So you can see that these components look very much what our computers look like today, right? Our computers take that input, they do the processing, they do some output, and there's a storage device like a disk unit, disk drive that maintains information. So at any point, an automaton is reading a single symbol of this string of characters. It's in a state. It could even be looking at some of the stored symbols if we have a way to store memory. And then at the end, it would produce a yes/no output. So we're just showing you the theoretical concept of what our push-down automatons or finite state machines are going to look like, or what they do. Now, when an automaton, or what an automaton should do in a given state, we want to have a transition function that defines if I'm in a state and I see this character, what's the next state that I go to? So for these examples, again, this is the layout of a transition statement. It's got transition of your current state, your input, optionally storage. We're not going to look at storage right now because we're only looking at finite automatons for the first couple weeks of the semester. We will get later in the semester to the push-down automatons, which have storage, but we're not there yet because we're only looking at regular languages. And the result is the new state that you advance to from the previous state based on the input character that you see. So here's an example of two transition statements. First one basically states that if you're in state 1 and you see an A, you transition to state 2. And if you're in state 2 and you see a B, you transition to state 3. Any questions? Okay. This diagram is incomplete when we talk about a DFA, deterministic finite automaton, or just a finite automaton. We'll get into deterministic and non-deterministic in a second. Typically, an automaton would have an arrow coming in to show you your start state. In this case, 1 is your start state, so we would typically have an arrow coming in. And 3 could be your final and accepting state. And if it was, it would have a double circle around it. And I'll show you an example of that. So again, if this machine had a double circle around 3, then the language that this machine accepts is an A followed by a B. Nothing more, nothing less. Okay. So as we define our automatons, we might have a case where if you look at the lower diagram, does somebody want to tell me what state we go to when we're in state 2 with a B?
You can go to both 2 and 3.
Correct. So the fact that there's, and again, you could have one instance of this, which we see the one instance of the B of 2 going to multiple states on a B, or you might have thousands of different ways to get to different states with different characters. But the moment you have a situation like this where there's a one way to go to multiple places on a single character, which we see that already from state 2 on the B, that makes this automaton a non-deterministic automaton. The one above is deterministic because you can only get somewhere from state 1 on an A, and you can only get somewhere on state 2 on a B. You can't get to multiple places. So the moment you can get to multiple places on the same character, that's what makes it non-deterministic. Any questions on that?
Is deterministic and non-deterministic related to like complexity time as well?
No, no, what you're going to find is with a non-deterministic automata, we can't write the code for the scanner. So what we're going to do in week 5, 2 weeks from now, is we're going to have non-deterministic automata that we're going to actually convert to a deterministic finite automata, and then you can write your code. And every non-deterministic automata can be converted to a deterministic automata. And we're going to go through a couple of exercises with that. And once you know how to do it, then you can do it for any NFA. NFA, I don't know if I've given you that acronym. So DFA is our deterministic finite automatas. A non-deterministic finite automatas, we refer to the acronym NFA. We drop the D. So NFA, non-deterministic, DFA, deterministic. I already stated that in order for your recognizer to be implementable, you must have a deterministic finite automata. And let's see, that's it for the lecture, but I do want to go and dive into a little bit of the non-deterministic finite automata that you're doing for this Japanese project. Again, when I first took this course on and I had learned that the project was a Japanese parser and translator, I panicked. I'm like, I can't do that. In reality, you're going to see that we just do a small regular language definition for some Japanese words. And it really is not as hard as it seems. And we'll go through that. So again, there's your Chomsky hierarchy, type 0 to type 3. And based on the homework, you're filling in details about those grammars. Okay, so for the project, which the first thing that's due, you don't have to worry about this yet. The first thing that's due is week 8, March 15th, I believe. I had recently changed this file because I still had the fall dates in it. You're going to email me as a group your DFA, your deterministic finite automata, which you're going to start with a non-deterministic finite automata. The regular language that's going to be accepted. So all of the words, the Japanese words that your projects are going to accept are going to be in the form of a vowel, or a vowel followed by the character N, or a consonant followed by a vowel, or a consonant followed by a vowel followed by an N, or a consonant pair followed by a vowel, or a consonant pair followed by a vowel followed by an N. And you can see at the end there, it's to the plus. And what does the to the plus mean?
One or more.
One or more. So we've got to have one of these. What is a vowel? It's what we know in the English language. The vowels are your A, E, I, O, U. But for this project, we also accept an uppercase I and an uppercase E. Because what you're going to find is there's a Japanese word, AGE, which is a vowel, a consonant, and a vowel. Okay. So that word is satisfied by our regular language because we said it had to have one of these. So it has a vowel, it has a consonant, followed by a vowel. So it's got this, and it's got this. Everybody see that? Good. You're going to also see that when, after you recognize a string and you determine that it's valid for this language, you're also going to tell the program is going to decide, is it of type word 1 or word 2? Okay. And that means that if the word ends in a lowercase vowel, it's of type word 1. If it's got that uppercase I or the uppercase E, we consider it a word 2. Again, this is just the type of word. We talked about consonants here. Our consonants are B, D, G, H, J, K, M, N, P, R, S, T, W, Y, and Z. So these are the consonants that we allow anywhere here. And a consonant pair is restricted to these sets of characters. A B followed by a Y, a G with a Y, an H with a Y, K, Y, M, Y, N, Y, P, Y, R, Y, or C, H, S, H, and T, S. So there's your consonant pairs. There's your consonants. We know what vowels are. Now, you're going to see that as you work with these finite automatons, for your non-deterministic, and then you convert it to a deterministic finite automata, does anybody see something special about the character N?
It's the only standalone constant.
Meaning this one?
Yeah, like it's the only consonant sound that can actually end.
So we use it there as a character that can follow us 3 of these things, or it could be a consonant. So I want you to keep in mind when you're working on the project that you're going to run into this where N can go to multiple states. So again, how do you make that non-deterministic to deterministic? We're going to learn that in a few weeks, but I just wanted to point that out. So now that you understand the regular expression, the set of characters that's allowable by the scanner, it will accept words that look like this. AOI, because A is a vowel, O is a vowel, I is a vowel, or Okashi. Okashi is a vowel, a consonant, a vowel, a consonant pair, the S and the H, right? A vowel and a vowel, I. So can everybody see how every one of these words that I have highlighted satisfies the allowable expressions? Anybody have a question on that? Good. So again, we're not worrying about the project yet, but I did want to go into this gory detail because I am going to show you the non-deterministic finite automaton that I'm going to provide you. I'm going to provide this to you, the class. I know this is messy. It messed up some people last semester, and I know exactly why. Because of the way the lines are drawn, you really can't see which line the characters go to. For example, this Q0 to QY is for the BMKN HPRG. Well, again, I'm not even sure at the moment. That's why I'm going to clean this up. But I did want to just show you a non-deterministic finite automata. And I'd ask you to tell me why it is. But again, what's not obvious to you is that this vowel here is this line going to Q1, and a vowel from Q0 stays in Q0. Everybody sees that? That from Q0, you can go to 2 places on a vowel. That's what makes this diagram non-deterministic. Part of the exercise for this project is you're going to convert this to a deterministic finite automata. And in future lecture, we're going to go through those steps as to how do we create new states, a combination of these states to make it deterministic. But some key things to point out with this diagram is the arrow going into Q0 says that our start state is Q0. Based on what I said earlier, can anybody tell me what the final state is for this machine?
It's Q0
Why?
because it's got two circles around it.
Good. What does final state mean?
It's the state that the word has to end up in order for it to be accepted by the machine.
Cool. You used the right word, accepted. The accepted state. Any other state, if you get into this machine, into Q0, and I also want to fix the diagram because you really shouldn't get into Q0, the final state, until we have one or more of, because we said it's to the plus, but I'll figure out how I'm going to fix that. If you end up in any other state that's not Q0, then you're going to essentially return no from this recognizer because it tells us that we don't have an accepted string. It's not valid. It doesn't satisfy these rules. So any questions on that? Good. What are some key things I want to point out here? You'll notice that the states are not just 1, 2, 3, like I showed you in those smaller examples. The states are Q0 for the start state. And then we use QY, QT, QC because they kind of relate to the character that leads you to that state. Like state QY, you only get to is if the consonant's going to be followed by a Y. QT, you only get there if it's a T, which is then going to be followed by an S or a, let's see, H for TH. Do I have that here? Give me 1 second. Let me just look at my other sheet. So TS is the only valid okay, so I'm still sharing my screen. T followed by the S is the consonant pair. And the reason it can go directly to state Q1 is because the consonant pair might have a vowel and then go to the accepted state, or the consonant pair might have a vowel then followed by an N. So the T, from Q0 on a T, we get to QT, which is a valid consonant. And it's either going to bring, oh, I'm sorry. Last thing I want to do is confuse you guys. And I'm noticing that T is a valid consonant by itself. So if we get a T, oh, right here. Okay, I had to get my eye straight. You see from QT, we can go right back to Q0 on a vowel. So that's a case where you have a consonant followed by a vowel. Or the T could be a consonant pair, so it's TS, which could be followed by a vowel and get us to the final state. Or the T and the S can be followed by a vowel, then followed by an N. And I don't want to go too much deeper right now. I really don't want to confuse anybody, but I hope everybody kind of followed my mouse as I moved around. And if you prefer me going to my tablet and drawing it, I will. But that everybody kind of see that flow where, based on the characters, we transition through the states, and we did wind up in Q0 when it satisfied the regular language. And if nobody speaks up, I'm just going to have to assume that everybody followed that.
Yeah, I got it.
Cool. So that's an introduction to a much more detailed finite automata. We're going to go through examples we're going to go through simpler examples. We're not going to have as many characters because here I'm showing you that Q0 to QY, you can get there from a B and M, a K and N, an HP, an R and a G. All this means is, again, it's a single character that allows us to transition from state to state. If I have multiple characters on that arrow, on that line, it just says, what are the different characters that move us, that we transition from that state on. I could have put commas in there to separate them. So I just want to make that clear. So again, it just shows you that the words we're going to be dealing with for this Japanese language are limited to the regular language or the regular expression that's defined here. I'm already handing you the non-deterministic finite automata diagram, which I'm going to clean up, I promise. And you're going to convert it to a deterministic finite automata. And you're going to see that once you have that deterministic finite automata, which really only adds like 2 or 3 states to this diagram, you can then go off and write your code that basically says, if I'm in Q0 and I get this character, I go to QY. If I'm in QY and I get this character. So it's just a bunch of if then else's, where you're saying in the current state, I allow for these characters. And if I get this character, I advance to this state. And then it just loops through while it's reading a character at a time. And at the end of the routine, it's going to return a yes, no. And does somebody want to remind me how we're going to determine whether it's yes, no?
If the last state is Q0?
Correct. Now, just to confuse you a little more, when you do combine, when you do convert this to a DFA, deterministic finite automata, you are going to wind up with a new state, Q0, Q1, and you're going to learn how we do this. And because Q0 is a final state now, any new state that you create that has Q0 will also be a final state. Again, we're going to learn all this. I am jumping ahead, but I think it's going to help set the stage for everybody for what we're going to be learning. So we are going to have multiple final states. So what are we going to want to do in our recognizer to determine if the string is accepted? Okay, we're going to want to check if we're in one of those final states. So the previous answer was if you're in Q0, it's accepted. But as we create the DFA, you're going to find we're going to have multiple final states. And we just want to make sure that the final state is one of those. If we're in any other state, it's not final, and we'll return no, because the recognizer will say invalid string. Questions? Okay. One of the exercises, we do have some time for this week, is just to show me an example of a regular grammar rule and one example of a context-free grammar rule. Again, let's just scroll up to here, where these are the examples of a context-free grammar rule. And these were the examples of a regular grammar rule. So if a couple of you want to just throw in the chat window, other examples outside of the ones that we see here in the lecture, just an example of a context-free grammar rule and a regular grammar rule. And I am sharing the screen that says right now on top, type 2 grammars, correct?
Yeah.
Yeah.
Gotta make sure. One time I was talking to a screen that I wasn't sharing, and wasn't fun.
What was the question again? I'm sorry.
So give me one example. Here's a bunch of examples of a regular grammar. And here's 3 examples of a context-free grammar. Just give me another example, one of each. Again, just to show me that the thought process. Let's start by just seeing some context-free grammar. So what I got highlighted right now are 3 examples of a context-free grammar. Show me another one.
Could one be like S goes to A?
Yes, it can, because it's any number of terminals and non-terminals on the right. Now, when you say S going to A, are you saying lowercase s or uppercase s?
Upper.
Upper, right, because as you can see right above there, only single non-terminals appear on the left. So again, I'm just ensuring that everybody sees, I know it's pretty plain as day. Context-free grammars are just a single non-terminal on the left going to any combination of terminals and non-terminals on the right. So if I were to create a new one, I could say G goes to C, 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 C. And of course, so there's an example of a context-free grammar. But when we talk about the regular grammars, we're limited to a single non-terminal on the left going to either a single terminal or a non-terminal going to a single terminal followed by a non-terminal. That's that H going to be A. Any questions on that?
Can you just repeat what you said one more time?
Sure. You see in the chat window, H goes to A, H goes to BA? That's the only 2 allowable production forms that you can have for a regular language. It either goes directly to a terminal or goes to a terminal followed by another non-terminal.
So it cannot go to multiple terminals?
It cannot. And again, that's kind of why I asked people to just type in the chat window what they thought, an example. But yes, it cannot be multiple. You can't have multiple terminals. You can't have multiple non-terminals. And there always has to be at least a terminal first, potentially followed by a non-terminal. And you're also going to see in a future class how we're going to wind up with grammar rules that for a regular grammar might not reduce to this. So we're going to have to go through a process of expanding out the grammar rules to make sure that we end up with a regular grammar.
Oh, so you can go from one grammar rule to another?
I'm trying to think how to answer that question. Yes, I believe we're going to start with context-free grammars, but we're going to make we're going to, I'm trying to think of the term, whether it's stratify, or we're going to find a way to make it a regular grammar by only having those last 2 formats, which is H going to non-terminal to terminal or non-terminal to terminal followed by non-terminal. So that's it for today. The homework is the recognizer and the generator. Anybody have any specific questions about that? Is everybody able to compile on Empress?
Yeah, I had a couple questions about for I want to say it's the generator
Okay.
one. The first one on the assignment, it says to have it every 20 or more spaces before it stops,
Okay,
or
let
lines.
me explain that. So you're gonna, the instructions were to generate all strings of length 1 with 0, 1, and 2, correct?
Yeah.
And then it wants you to generate all length 2 strings with those characters, right? So the next, so you're gonna have 0, 1, 2, 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2, right?
Yeah.
And then you're gonna do length 3, all strings of length 3. What I'm saying with the 20 is you also know that I only want you to output to the screen which of those strings we just talked about were valid for that language. The language being only binary numbers, right?
Yeah.
So 20 just means after you've displayed 20 valid numbers from that generation process, you can stop your program. That's what the 20 means.
Okay, because that's what I was doing. I just noticed with the like sample output you gave us, it stopped every time the binary was all ones. So I didn't know if you wanted that or if
Oh,
it was fine to stop after
what
20.
that was, it was just basically so that the screen doesn't run off forever.
Yeah.
It was a way of just pausing the program, hitting some character, then seeing the next set. And then at some point you'll control C, or you'll actually say, input the word exit or end to stop. You choose what you want to do.
Okay, so just so long as we're still showing all the binary, then it's fine.
On the binary and show me at least 20 of them. That's what I want to see, at least 20. If you show
Okay.
me 500, great. Do I want to see all 500? So hope that answers the question.
Yeah, and then I had another one. It was more of just about actual like coding.
Okay.
When I implement the loop to show 20, so I have a counter going. If I continue to count, so I could say it goes to 20 and then it stops and it checks. I had it where in my if statement, I was checking if count modulus 20 equals 0. So if it returns 0, then it would know that 20 went through, so it would show. It always did my print statements twice when I did that. But then if I reset the count to 0 each time and just check if count is 20, then it only prints once, which is what it was supposed to.
Okay, you're getting me because I would kind of have to see the
Um,
code. I'm trying to think, but sounds like you want to do the second option, which is working properly. But
Yeah, if I checked it with like count or not equals 0, but equals 20,
if it equals 20, or
and
basically you want to say when it exceeds 19, or when it is equals to or greater than 20, that's where you want to exit out.
yeah, and then I would just reset. I was having it where you could like enter into exit or continue. And so then it would just reset the count to 0 and then count up to 20 again to stop.
But that's when it was displaying twice.
No, if I did modulus, if I did it like this, and so then instead of resetting count, it just continued to go up. That's when it would display the question as well as it taking input twice in a row.
Not sure. Anybody have any ideas why the modulo 20, is that going to be 0 when it's 0, or is it only going to be 0 when it's 20, 40, 60, 80?
I believe it should just be when it's 0, 20, 40, 60, 80 to 100. And otherwise, I think it should just return 1.
Okay. If you want to email me a snippet of the code just to have me glance at it, I'd be glad to. But if it's working where you check it,
Yeah, I believe that it should equal 0, which is kind of what I wanted. But I don't have
So
sample.
I actually
output.
had a similar issue when I was writing mine.
okay.
And it was, at least in my case, it was because the recognizer, you're checking all the combinations of the like 0, 1, and 2. So even when you, like if you got to 20, for example, and then the next string wasn't valid, your count would still be 20. And so it'd print the previous one a second time. At least the way I fixed it, I had some Boolean that said, oh, I previously had the current string is a valid one. And so like print it, if not, set it to false so that it doesn't repeat.
Or you only want to count. you want to increment the counter only when you've recognized a valid string.
Yeah, that too.
That may be what's going on.
Because yeah, I had like a separate if for when it would count up for if it was counted. It was just literally just for my loop. It did that, and it was only that one line for the if that if I changed that, it would work. Everything else was the same.
Okay, but you did get it working, right?
Yeah. If I do the if count equals 0, then it works.
Okay. Again, if you just want a second pair of eyes, in the industry, we do peer reviews. I mean, I've talked about that early in the semester, maybe not. Having somebody look at your code, certainly in the industry, we as developers, we could potentially miss something, and you always want somebody else to peer review your code. And I'm talking about in the industry because when I worked working with aircraft, finding a problem early in the process during a peer review by your peers is so much cheaper than implementing an issue in the code, then sending the code out to the aircraft, and then sending the aircraft out for flight test where they got to get personnel, they got to get flight time, they got to get fuel. It costs sometimes $50,000 to $100,000 just for a test flight. And to find a bug then is really horrible. So peer reviews in the industry, any company you go to, if they're not doing peer reviews, you mandate that they do them. And peer reviews are not meant to criticize people's coding styles, to say, hey, you wrote some shitty code here. No, it's really just to get another pair of eyes from your peers, at least 3 developers, to make sure that something isn't coded improperly. In the case of what I'm seeing in the chat window, certainly using a double equals versus a single equals is a big one, right? Everybody knows that if that double equals were a single equal in an if statement, that's a bug, right?
Yeah.
So things like that. So yeah, like I said, if you want to email me the code snippet, just have another pair of eyes and see if I can figure out why I was doing that, I'd be glad to. But again, I'm just talking from industry, why peer reviews are really important, especially when you could save a lot of money finding a bug much earlier on.
No, I'll email it to you because as far as I can tell, it should work unless I'm missing something with modulus, which I might be.
Yeah. Okay. That's all I had for today. For the programming, again, I'm asking you to generate the output files, include the output files, the source code, and that homework sheet. And that's it. And then we've gone over the homework that's due next Friday, which is the 19th. So
Thank you, Professor.
You're welcome. I hope everybody has a good week. See everybody on Monday.